Lots of new terminology in this section. So we're going to talk about diagonalization in general, but first let's talk about similar. So two matrices are similar. So A and B are similar if A can be written as PB, P inverse. That's kind of a weird thing, isn't it? Okay, so first let's just play with determinants. So if I take the determinant of A, then I'm going to substitute what A is equal to. So that's PB, P inverse. Whoops, I didn't mean to make that inverse so big. Okay, and then I'm going to use what I know about determinants. I can separate this. I don't need parentheses there. I can separate it, and then what do I know about this, this, and this? Each of them are numbers, and so I can move numbers around. So I'm going to move this. And then I'm going to join these together. So P times P inverse, kind of the opposite of what I did in the beginning. Then I know that P times P inverse gives me the identity matrix. And the determinant of the identity matrix is just 1. So I got from determinant of A to determinant of B. Okay, so this is a unique relationship. We're going to find out what this is. And so why we like this is because it's an easy way to compute the matrix A to lots of powers. So let's look at A to the fourth. So let me just do it over here for a second. So A to the fourth, if every time I have an A, I write PD P inverse. So I'll have PD P inverse times PD P inverse, PD P inverse, PD P inverse. Okay, so 4 of them. Look at what I've got here. So this P inverse times P gives me the identity matrix, right? So that's a 1, and so this D is multiplied times this D. What do I see here? These two multiply to be 1, so I have this D. And then these two multiply to be 1, so I have this D. So what I end up getting is P D to the 4th power P inverse. And so here's my P and here's my D. So let's just take a look at what's happening. So if I want to do A to the 4th, that would be my matrix P, my matrix D multiplied times itself 4 times. So think about it. Think about what happens when I multiply this times itself even once, right? So D squared. So I would get 4, 0, 0, and then I would get 1 times 1, which is 1. So the D squared turns out to be this squared, right? So let's make it up here. D squared turns out to be 2 squared, 0, 0, 1 squared. So I'm thinking you can probably figure out D cubed will be D cubed, 0, 0, 1 cubed. So what's D to the 4th? This to the 4th and this to the 4th. And then P inverse, and I didn't go figure out P inverse, so I'll just write P inverse here. Okay, so the point is that instead of multiplying, right, 3 times 4, 12 matrices together, I'm going to have 3 to multiply together, which is so much easier, even if you're doing it on a computer. So that's why we want to be able to write A as PDP inverse, because this is the point. We can easily calculate A to the n. Okay, so let's go into what that process is called. So that's what this diagonalization, the title of this section, is. So a matrix A is diagonalizable if and only if A has n linearly independent eigenvectors, and where we get these matrices P, D, and P inverse. So D will be the diagonal matrix, right? Like this is D, a diagonal matrix, with the eigenvalues of A that are on the diagonal. And the P matrix is made up of the linearly independent eigenvectors, and they will correspond. So let's look here. So this is my matrix A. This is P, D, P inverse. So again, this is A. this is P, this is D, and this is P inverse. All right, so this is D right here. So these diagonal entries are the eigenvalues. So here I have the eigenvalue of 5. This is the matrix P right here. So this would be the eigenvector that goes with the eigenvalue of 5. Moving on to the next one, so I see the eigenvalue of 1 written twice. So what that means is that there's 2 vectors that go with the one eigenvalue of 1. So this is an eigenvalue or eigenvector, and this is an eigenvector that go with the value of 1, because you've seen an eigenvalue be 2-dimensional. So this is not unique. I could switch the order of the 1s and the 5s, and I would just switch the order of the vectors in the P. But you just have to make sure that they correspond. All right, let's talk about, okay, so the diagonalization theorem says, if I have a square matrix, it is diagonalizable if and only if A has n linearly independent eigenvectors, not eigenvalues, eigenvectors, where I can make this A equal PD P inverse, where D is the diagonal matrix with the diagonal entries being the eigenvalues of the A, and then the eigenvectors are in P. And so then they're linearly independent.